Once you join, sign your attendance. Good evening, everyone. I think I can see Rejoice now. Rejoice, you are welcome to the class. Once you join, sign your attendance. Indicates that you are there. Otherwise, if I catch you tomorrow. Remember to like this video, okay, and then share it to your friend. Share it to somebody so that somebody can come over and learn, all right, from this channel of excellence. You're welcome to this class. In our chemistry class today, we are going to give attention to preparation of hydrogen. And so, I welcome you to this channel of excellence, the GMAETS 41. Let's move on quickly. There is no time to waste, okay? In the preparation of substances, especially when you talk about non-metals, because this chemistry class is going to focus more on preparation of non-metals, at least within these few days, or let's say this week. So we trash that out, okay? And we're going to take them bit by bit, so at least you dear friends can capture the things that your examiner wants you to know about these non-metals. So in each of the discussion of preparation and properties of these non-metals, we are going to learn, number one, how to prepare them, the laboratory method of preparing these substances. For example, we are dealing with preparation of hydrogen gas, okay? So you are expected to give attention to the laboratory preparation of hydrogen gas, and then as much as possible the industrial preparation of hydrogen gas, okay? Then also you should give attention to the physical properties of these substances. Like I said, this class is focused on hydrogen, so you're expected to learn the physical properties of hydrogen. And then you give attention to the chemical properties, where of course you deal with the reactions of hydrogen. Then not to forget, as much as possible, the uses of these substances. So for each of the non-metals you're going to treat, you're expected to give attention to them. Hydrogen, chlorine, oxygen, nitrogen, sulfur. Then plenty, 5 of them. And for each, like I said, method of preparation, laboratory method, industrial method, if applicable, physical properties, chemical properties, then you talk about the uses. So please remember this as we kick off our class. Hydrogen. That is what we want to deal with. I hope we have joined the class. You're welcome, everyone. I may not be able to call all of the names, but I can see your signatures. Okay, I can see your signatures. You are welcome to join the class. So let us kick off. We don't have time. Preparation of hydrogen. We shall start with laboratory preparation. Laboratory preparation of hydrogen. Laboratory preparation of hydrogen. But first of all, let us get a little background knowledge of hydrogen. Which scientists actually discovered hydrogen? Which scientists discovered hydrogen? How is he called? So take note of that. Cavendish. All right. Cavendish discovered hydrogen. Cavendish discovered what? Hydrogen. And then there is something about hydrogen that was also found in the process. Okay, it was discovered that if hydrogen mixes with air, it is flammable. Yeah, it is flammable. So you want to take note of that. Hydrogen is flammable. And because of that, a scientist known as Lavoisier named it hydrogen. Remember, the person that discovered it is Cavendish. Cavendish discovered it. But the name hydrogen was actually given by Lavoisier, right? Lavoisier is a French name. I think the correct pronunciation is Lavoisier or whatever. I'm not interested in the pronunciation. Lavoisier, okay? He named it hydrogen, Lavoisier. Lavoisier. He was the one that named this gas hydrogen. Take note. And what is the meaning of hydrogen? Hydrogen means water former. Hydrogen means what? Water former. So you take note of this little background, okay? Take note of this little background. The person that discovered hydrogen is Cavendish. The person that named it is Lavoisier. And hydrogen means what? Water former. Just like halogen means salt formers. Let us now move on to the preparation of hydrogen in the laboratory. I hope we are ready with our writing materials. Sometimes you may not have enough time to copy whatever I say. If I write on the board, you can screenshot. If I write on the board, you can do what? Screenshot. Is that okay? Sometimes too, of course, you follow up with the dictation. You have to be as fast as you can. This is an online class. At the end of this class, a copy of this live class will be made available. So if you are not able to meet up some things in writing, please check back so you can update your notes. Remember, this is not physical class, and so there will be no time to continuously repeat the same thing over and over again. But don't be discouraged if you are not able to meet up some things. A live copy of this will be made available. Laboratory preparation of hydrogen. Now, hydrogen can be prepared in the laboratory from any of the following methods. Any of the following reactions I am going to mention is a laboratory preparation method of hydrogen. You are expected to know that. Please take note. Number one, the action of zinc, metals on acid, metals on mineral acid. The metal usually used is zinc in this case, okay? So one of the laboratory method of preparation is action of metal. Good example of metal we can use there is zinc, all right, on mineral acid. A good example of a mineral acid we can use is hydrochloric acid. This is one method of preparing hydrogen gas. Don't worry, we are going to look at the chemical equations, or perhaps I could still even write out the chemical equation in each case, so that the next thing will not be for you to see the diagram, because it's very important if you're preparing for JAMB, if you're preparing for WAEC, to be able to, create a mental picture of the laboratory setup. It's very important for you to be able to do that. So I will try as much as I can, if possible. If I'm not able to, dependent on time, please, I will encourage you and urge you that after the class immediately, you can go to Google and type. Are you following right? Diagram for the laboratory preparation of hydrogen from the reaction or the action of metal on a mineral acid. The other method also, you can type that directly and Google will show you the diagram. Apart from that, your textbooks also have the diagram. Your past questions can also show you the diagram as well too. Are you following right? So take note of that. Now, action of metal. Example, zinc on mineral acid leads to the production of hydrogen in the laboratory. Look at the chemical reaction equation. Zinc is solid, and then if it reacts with a mineral acid, hydrochloric acid, which is aqueous, of course, this is what is going to happen. This compound would split here. There is going to be a bond breakage between this hydrogen and chlorine. And of course, zinc is a positive substance. It's a metal. It is going to pick chlorine. And we expect that zinc chloride will be formed. Zinc chloride will be formed. And this is the correct chemical formula of zinc chloride. Then after that, our hydrogen gas will be given off. H2. Hydrogen gas will be given off. This is in aqueous form. And then hydrogen gas. This is the chemical reaction that leads to the preparation of hydrogen gas in the laboratory through the action or by the action of a metal on mineral acid, right? So a mineral acid and a metal react. The metal used mostly is zinc, as I've mentioned. We are going to look at the second method of preparing hydrogen, which is the action of sodium on cold water. Sodium as a metal reacts with cold water, and of course this reaction is extremely vigorous. The reaction is vigorous, it occurs fast. So when sodium reacts with cold water, hydrogen gas will be given off. The resulting solution will become alkaline in nature because sodium hydroxide will be formed in that process. Please permit me to check the camera, number one, the network situation, to be sure that the network is still on, and then secondly, to be sure that it was able to capture this part. Let it not be that something cut off. All right, so I'm going to adjust this a bit. Good. Good evening, all of you, and welcome to join the class. I can cite all of you, please. I'm sorry I cannot be able to call your names, but let's see, should I attempt? I have Rejoice here, your signature has been seen. Angel, your signature has been seen. In Mindset Africa, I really cannot recognize you. Omali Adobe, your signature has been seen. Weke Antonia, your signature has been seen. George Arinze, your signature has been seen. But George, this is not your class. Okay, I think you're taking Math 101 in Unizik tomorrow, so go to your class and go and learn. Anastasia, your signature has been seen. Oji Jennifer, Anastasia Woshi, and then we've got Chidera Promise, Ume Victor, Chioma Wachiku Kulde, Kudepi Koma, I guess from India if I'm not mistaken, or is it from Nigeria? Prime, I can cite you. Chinedu Mwogbo Miracle, and then Onyinyechi. I think I've tried. I've been able to recognize all of you. So you're welcome to join the class. Everything is showing, the network is cool. So we move on to the second method of preparing hydrogen. We are done with the first method. The second is the action of sodium on cold water. Action of sodium on cold water. Action of sodium on cold water. Okay? Do I really need to balance the first reaction equation? Well, it's just for you to know that hydrogen is given off, hydrogen gas. But perhaps let me just balance it. I guess here we are going to fix 2 because we have 2 chlorines here, 2 hydrogens. So you fix 2 here. Zinc is 1 in the product, is 1 in the reactant. The reaction is balanced now. Action of sodium on cold water is another laboratory method of preparing hydrogen gas. Let us look at the reaction equation quickly. So here you have a sodium, all right, sodium pellet. You have sodium pellets just in solid form. And then it reacts with, I think I should use another shade of marker to write this. It reacts with our cold water. So this is sodium plus cold water, H2O. And then what is going to happen? You see this water is going to split into hydrogen and hydroxide ion. Hydrogen ion and hydroxide ion. For the GMAETS 41's JAMB and WAEC students in our physical lesson, I've actually explained this concept from acid, base, and salt. We treated that, where we said that water is usually formed when hydrogen ion from an acid reacts with hydroxide ion from a base, a reaction process that is called neutralization, and then water will be formed. So water, which is composed of hydrogen and oxygen, actually, this is how the components come together to form water. Hydrogen ion and hydroxide ion. So, this water is going to split to these ions. Therefore, sodium will pick this OH. Sodium is positive, we know, as a metal. This is hydroxide ion. It's a radical, negative. So, this positive guy is going to be attracted to this negative guy, which means that sodium hydroxide is going to be formed, like I rightly told you people earlier. Sodium hydroxide will be formed, and of course hydrogen will be given off as a gas. Hydrogen will be given off as a gas, hydrogen gas. This is aqueous because it is in solution form. This is the reaction equation leading to the formation of hydrogen gas by the action of sodium on cold water. Let us see if we need to balance up this. Let's see if we need to balance up this. Hydrogen is 2 in the reactant, as you can see. And how many hydrogens do we have in the product? Here in sodium hydroxide, we've got 1. Here in the hydrogen gas, we have 2 atoms of hydrogen gas. So altogether, 1 plus 2, we have 3 atoms of hydrogen gas. Now, if we have 3 atoms of hydrogen gas, we could have to come here. We might have to come here and then talk about making this guy 3. Making the hydrogen in water to become 3. But one thing is, can you multiply these 2 atoms of hydrogen in water? Can you multiply 2 by any whole number? I repeat, can you multiply 2 by any whole number to get 3? Is it possible? It is not possible. I remember saying this in our physical lesson, that in balancing chemical reaction equation, one thing that has been observed is that most times you target numbers. You target even numbers in balancing. I am not saying it's a general rule, but in 90% of the cases this happens. So since you cannot multiply 2 by any number to get this odd number 3, it means you have to increase this to an even number. If you cross 2, the next number you meet is 3. We can't target it here. We can't multiply 2 by any number to get 3, by any whole number to get 3. Therefore, we target the next higher number, which is 4. What can you multiply 2 by to get 4? You'll agree with me that you multiply 2 by 2 in order to get 4. So, water will become 2 molecules here. And if water becomes 2 molecules here, check that hydrogen is now 4. 4 atoms of hydrogen in the reactant. In the product, we have 3 atoms. We have 3 atoms. We can actually make up this to be 4 if we attach 2 molecules to sodium hydroxide. I had to attach 2 molecules to sodium hydroxide because oxygen here in water, in the reactant, oxygen is 2 molecules. So in the product, that oxygen also has to be made 2 molecules. That, of course, is one of the greater reasons why I decided to fix 2 here, and again, to make hydrogen to be 2 in this sodium hydroxide, so that 2 hydrogens added to 2 hydrogens will give us 4 hydrogens. And that balances up hydrogen here, and oxygen automatically also balances. Remember, the number of molecules affect each atom that you have in the compound. Number of molecules affect each atom that you have in the compound. But atomicity only belongs to the element that number is written as a subscript. Sodium has to be balanced with attaching 2 here. So we are done with this guy, and you notice that hydrogen gas was given off. I hope you are learning, right? We are treating the laboratory preparation method of hydrogen gas. In your exam, JAMB, that is UTME, WAEC. By the way, what's the difference between JAMB and UTME? WAEC and WASE. So let me tell my friends that. JAMB is the name of the organization, Joint Admission and Matriculation Board. The name of the exam itself is UTME, University Tertiary Matriculation Examination. Then if you come to WAEC and WASE, WAEC is the name of the exam board, the name of the organization. WASE is the name of the exam, West Africa Senior School Certificate Examination. That is not the focus of this class anyway. Let's continue. The next method of preparing hydrogen in the laboratory is the action of steam on red hot iron. So reaction between iron and steam. Please copy out this. You can screenshot to beat up, like I said, in case you have not been able to write it down. Okay, you can screenshot. Let us move on. Let us move on. Let us move on. Someone asked a question. This reaction is which type of reaction? We are not treating types of reaction in this class anyway, but this reaction is somewhat a displacement reaction. It is a displacement reaction. I did not take note of the person who asked the question anyway, as per the name, but this is displacement reaction. However, this class is not focused on type of reaction. It's not. Under redox reaction, we treat types of reaction, and we are not yet taking redox reaction. So the next method, like I said, is the action of steam on ion. Are you following right? When ion reacts with steam, so the action of ion on steam leads to the production of hydrogen gas in the laboratory. In the process, an iron oxide compound is formed. An iron oxide compound is formed, which is called iron 2 di-iron 3 oxide. Iron 2 di-iron 3 oxide. Let us look at the chemical reaction equation leading to the preparation of hydrogen gas in the laboratory by the action of iron on steam. I said, your examiner, if they're asking you this question on methods of, you could simply be asked, which of the following is a method of preparing hydrogen in the laboratory? They must not specify in the laboratory. It could just be open. Which of the following method is used in preparing hydrogen gas? Or you might be asked this, which of the following method is not used to prepare hydrogen gas in the laboratory? It's not. Which means maybe 3 options provided will be methods of preparing hydrogen gas. Then one of the option would be a useless option. Yes, a method that is not used. That is why you should know all of this method. Let's move on. Number 3, action of ion on steam. Action of ion on steam, which means you have to heat that liquid. Remember that water converts to steam when you heat water, up to its boiling point and beyond. It starts vaporizing, and that vapor form referred to it also as steam. When ion reacts with steam, the action of ion on steam leads to the production of hydrogen gas. And like I said, there is a compound that is formed there also, iron 2 di-iron 3 oxide. Let us look at the reaction equation. Iron Fe, it is solid. The ion is expected to be red hot. You need to indicate that as a note. The ion is expected to be what I said, red hot ion. Red hot means that you have to heat up the ion to a very high temperature. You have to heat up the ion to what? A very high temperature. Red hot. Have you ever seen iron in red hot state? Of course, you will heat it and the iron would start shining red, fire color. So take note of that, please. The iron is expected to be red hot. So we are going to react this with steam, H2O. All right. So let us look at the product that is formed here. I've told you the products already, so it's just for us to write them out. So we have iron 2 di-iron 3. This compound is called, this is 3 please, and then 4, sorry. This is iron 2 di-iron 3 oxide. That is the IUPAC name. So it's going to add up to our hydrogen gas, which is liberated. Hydrogen gas is liberated, is given off. So this is the chemical equation leading to the formation of hydrogen gas in the laboratory. So we have this. I told you that compound is called what? Iron 2 di-iron 3 oxide. Take note of the name. Iron 2 di-iron 3. oxide. So you may choose to balance. Oxygen is 4 here. Iron is 3 here. Okay, let's deal with that of oxygen first. Oxygen is 4 here. In the reactant, oxygen is 3. So we have to attach 4. These 4 molecules of steam will now be affecting this oxygen, making this oxygen to be 4. Of course, because this water here is steam, it is going to bear the state gas, because the steam state of water is gaseous. Alright, this is aqueous, because it will be in solution form, right? And then you have your gas. Is this meant to be aqueous or solid? Remember, it's reacting with steam, so it won't dissolve. It's reacting with steam, so it is not going to dissolve. It's not going to dissolve. To remain solid. It's just like when you have a solid substance. The iron is solid. You have this marker and you splash a gas around it. Steam is gas. So this won't dissolve. Are you following, right? It won't. Therefore, the iron 2 di-iron 3 is in solid state. We are trying to balance. What else is left? Hydrogen here has become 8. You can see that, which means coming over here, balancing the hydrogen gas, we'll have 4 molecules of hydrogen gas. And then, of course, you see that iron is 3 in the product. Come to the reactant, and then you fix 3. Please take note, these are the 3 key methods of preparing hydrogen in the laboratory. So store this information in your brain, store it in your kidney, store it in your pancreas, store it in your liver, so that you will not forget. It is now time we are going to look at the diagrams. I'll be very fast in sketching these diagrams. I want to make reference to it because in the diagram there are also examination questions that you can be asked based on laboratory preparation of hydrogen gas. These 3 methods have special diagrams for each of them. So if you are given any of the diagram, your examiner has the right to ask you which of the following, as in the diagram above shows, or the diagram above represents the laboratory preparation or simply the preparation of dash. The diagram above represents the preparation of dash. So you need to be aware of the diagram. As I sketch the diagram quickly on the board, try to create a mental picture of the diagram. Because creating a mental picture of the diagram as if you're seeing it in space will now help you in your JAMB. If you're given a particular diagram, if it is related, you know what that diagram is used for preparing. In WAEC, when you sit for it, in theory, an examiner can ask you, draw the diagram for the laboratory preparation of hydrogen by the action of maybe sodium on cold water, iron on steam, or perhaps metal, say zinc, on mineral acid, say hydrochloric acid. Let us take a look at the diagram, please. Make sure you finish up what is on the board. Make sure you finish up what is on the board. Make sure you finish up what is on the board. Remember, this class is not expected to go beyond 1 hour, right? At worst, 1 hour 30 minutes. Is it at worst or at most? 1 hour 30 minutes. Okay, this is the hour that your level takes. I'm going to wipe this diagram now. Is it the diagram or the write-up on the board? I'm going to wipe them. So we have seen the methods of preparing hydrogen in the laboratory. Let us sketch the diagrams quickly. Let us sketch the diagrams quickly. There are some questions I just saw. Alright, but I can't attend to those questions, especially not now. Somebody asked a question on how do you clear government in 1 year or something. Another person was asking a question at micro level. So these things, they have nothing to do with what we are learning now. It will be off requirement to be talking about it. Please take note. Once you join this class, be ready to operate with what is happening here. This class is targeted to prepare students for their forthcoming professional examination. Some of all these are personal questions. You can direct them to GMAETS 41 directly. Preparation of hydrogen gas from the action of metal, example zinc, on mineral acid, example hydrochloric acid. So the first, we've got this. The first one, action of metal on mineral acid. So we have a flask. We have a flask that will contain the reaction mixture. All right. This flask here, the bottom here looks like my head, big head, right? So let us continue. And then, of course, you have your tissue funnel through which you will channel the acid, through which you will pour the acid, Are you following, right? So the tissue funnel, thing is called tissue funnel. So you pour the acid here. Already the zinc solid will be inside this flask. So let me say that you have your zinc here. You have your zinc, and then the acid drops and trickles down this way. The acid enters and then reaction begins. Then of course you have another, delivery tube. Okay, the delivery tube goes this way. Then usually you have a chamber here. Goes this way. And then comes down. You have your collection vessel here that contains water. You have your collection vessel here. In the collection vessel you have a collection tube, test tube, that is turned upside down. You have a test tube that, like I said, I'm sketching anyway, so I don't need to wipe off anything here. So you have your test tube, and the test tube is turned upside down, like I said. So this thing will have to come this way. So the test tube is turned up so that this delivery tube goes in like this. Have this thing close up this way. Then you have water. You have water here. You can get a clear diagram of this from your textbook, or you Google it. Are you following, right? This is your test tube. Then on top here you have your hydrogen gas. So I'm going to label this hydrogen gas. That's your hydrogen gas. Inside this reaction vessel, like I said, this is zinc. And then this is your acid. Let's say HCl. As it trickles down, the mixture here is a mixture of zinc plus HCl. The chemical reaction equation which we had written earlier. So you notice that in the collection of hydrogen, because here the hydrogen will bubble out. Once the hydrogen is produced here as a gas, gas naturally will move randomly. So we expect, let's say that the hydrogen gas, after this reaction, it forms, and then it will follow this tube. This delivery tube. As a gas, it's going to bubble through the water. If it bubbles through the water, it's going up. It's just like you having gas in water, it bubbles through. It's going up. And because hydrogen is very light, In fact, hydrogen is the lightest known element so far. The hydrogen will keep bubbling to go up. So it will displace water down. Alright? Water is going to be displaced downward to allow the hydrogen gas to move up. That is why this colorless part is your hydrogen, because of course hydrogen is a colorless gas. It is also odorless. So it will be collected at this point on top of the water. So the method of delivery, examiner may ask you of it. The method of collection rather of hydrogen. An examiner can ask you, hydrogen gas is collected by what method? Looking at this setup and the fact that the hydrogen goes above the water, it means that water is displaced downward and the hydrogen is collected by upward delivery. Method of collecting hydrogen gas. Hydrogen gas is collected by downward displacement. Hydrogen gas is collected by downward displacement of water. Displacement of water. And this is also the same as upward delivery. It is obtained by upward delivery. Upward delivery. Not upward delivery of water. For water, the water is displaced downward. Then you now have an upward delivery of the gas. So this is the diagram that shows the laboratory preparation of hydrogen gas by the action of zinc on what? Mineral acid. Take a look at this. You can screenshot. Like I said, you can also Google it, look through your textbook to see the diagram further, and then create a mental picture of that diagram. For example, the way you've seen GMAETS 41 before, at least you have a mental picture of the face of GMAETS 41, of course, of the handsome face of GMAETS 41, by the way. Don't mind me. So try to create a mental picture of this guy for your exam's sake. I'm going to wipe this, then we draw the second diagram. Action of sodium on cold water, leading to the preparation of hydrogen gas. Finish up, you can screenshot, let me wipe that. You can screenshot, let me wipe that. Angel Olawale, please drop me your WhatsApp contact. I need your coaching in Physics 101. I am in 100 level, University of Ibadan. Alright, Angel, my WhatsApp group, is a WhatsApp group rather, GMAETS 41's WhatsApp number is showing on the board directly. Look at it. So you contact GMAETS 41 and then you can tell me how you wish that I assist you. By the way, mind you that all your works in University of Ibadan, your Math 101, your Physics 101, and Chemistry course, depending on whether you are offering them, they are all well loaded completely. All the topics well explained on this channel. So Angel Olawale, take note. Let's move on to our second diagram. This time around, the diagram that shows the action of sodium on cold water leading to the preparation of hydrogen gas. I'm wiping this diagram, please. Don't forget the method of collecting hydrogen. Downward displacement of water, which equates upward delivery. And the reason is because hydrogen is less dense than air, right? Hydrogen is what? Less dense than air. Usually, gases that are less dense than air, they are collected usually by upward delivery because they will displace water downward and then move up. That's the whole idea of this downward displacement of water, which is synonymous to upward delivery. Let us look at our second diagram. In the second diagram, we have a vessel. In that vessel, there is water, and then you use a spoon to drop your sodium. The sodium is in solid form. Once you drop it, the reaction picks up immediately. It's very vigorous. It doesn't waste time. And you start seeing the gas coming out, smoke-like somehow. But of course, it is colorless. And then there is an inverted test tube to help collect the gas. The gas moves up. Like I said, you collect it by upward what? Delivery. Let us look at the diagram. So this is a reaction vessel. Here you've got your water. You have your water in this reaction vessel. You have your water in this reaction vessel. I'm sorry I did not label the water in the first diagram. That collection vessel inside, like I mentioned, it's water. Okay, so take note of that. Then, like I said, you have a test tube. You have a test tube inverted this way. Are you following right? Then, of course, you have a spoon. I don't know if this is the spoon that I used to eat. Whatever the case is. Right? So this is the spoon. This is the spoon, has sodium in it. Is it has sodium in it or on it because you use the spoon to collect the sodium? It could be something like a spatula. There is this small metal spoon-like material called a spatula. Spatula. S-P-A-T-U-L-A in the laboratory. Use it, collect the sodium, and then just drop. Are you following? Inside the water in this vessel. So once the sodium enters, reaction kicks off. This is your sodium, like I said. This is your sodium metal. Then, of course, this is your water. This is your water, H2O. Cold water, let me indicate. Cold water. So once the reaction takes place, hydrogen will be collected here. So I'm going to label this as your hydrogen gas. I'm going to label it as your hydrogen gas. So that is that about how you prepare hydrogen by the action of sodium on cold water. Is there anything that is to be labeled? This is your spoon, like I said. Spoon, right? This is test tube. It is inverted. It's not a main area that an examiner can ask you a question on anyway. What is this? It's a test tube inverted, but it's not necessary. The sodium, the water, and the hydrogen gas that is collected. These three are the main focus if an examiner is testing you on this. In fact, in your exam, this diagram can be set up. You may have this set up, and then this is labeled as water. This is labeled G, and coming to this, they might label it as X. Say this, the sodium. They might label it as X, and they ask you in the diagram above, X represents dash, and your answer will be what? Sodium. Or perhaps this is labeled as your water, cold water. This is labeled as sodium, and then here perhaps it is labeled as X or Y or Z or whatever alphabet that your examiner wants. Take note. As a result of the fact that this is sodium in water, what you are going to produce here is hydrogen gas. So whatever alphabet that is used in labeling this part, that alphabet, if you are asked what it represents, it actually represents hydrogen gas. Finish up this. You can, if you are sketching, fine. If you are screenshotting, fine. Let's move on to the next diagram. Let's move on to the next diagram. Naomi, you are welcome to join the and see your signature. This crater cave, right? The name is not familiar. This crater cave. Good evening. You're welcome to join the class. We are moving on. We are moving on. Remember, there is no time, and always remember that this is GMAETS 41. Let's move on to our third diagram. When you are feeling weak over there, remember what to say. GMAETS 41. And the sleep will clear off. Your eye will become clear, and everything that you are learning will be sinking in. Your whole body will absorb them. Okay? So I'm wiping this. Let's move on to the next diagram where you prepare hydrogen gas in the laboratory by the action of ion on what? Steam. So just imagine this. We're talking about ion on steam. And I told you that the ion has to be red hot, which means you need to heat up that ion. That's interesting. Now, how do you produce steam? Steam is obtained from water. So you would have to have a flask, right? Could be a round bottom flask where you will heat water, liquid water. You heat it so that it can vaporize and produce what? Steam. Once it produces steam, by the way, the flask that contains the water could be a flat bottom flask in conical form. One can use any of the flask, it doesn't matter. Okay, it really doesn't matter. Now, as you heat that flask, the water will heat up to steam state. And of course, once liquid water, right, becomes steam, the steam moves. So as the steam moves out from the vessel where you heated that liquid, that water, the steam will start moving, and there is going to be a delivery tube through which the steam will pass. As the steam is passing the delivery tube, you have a part in that delivery tube that contain ion filings. Are you following, right? And that ion filings there will be receiving heat. Because like we said, the ion has to be in what? Red hot state. So once the steam passes that ion, the reaction will take place. As the steam is passing over that ion, the reaction will do what? Take place. Once that reaction takes place, the steam is passing over the ion. Automatically, the ion is reacting with the steam to remove hydrogen gas. Which means once the steam gets to the ion, what is now going further is hydrogen gas. Then you now collect that hydrogen gas by downward displacement of water, which equates to upward delivery. So from what I explained, we should be looking at a diagram that looks like this. Let us say that this is a stand, okay, where you heat. So there is heat here. You are heating, just like what the flask will be placed on top, and heat passes through. So we've got this flask. We've got this flask. We've got this. So we've got this flask. In the flask, you have your water, like I rightly said. And because you have your water, you could be dropping the water through this thing, okay, that looks like a pipe. So we have water here. There is the delivery tube now. We have the delivery tube. We have the delivery tube that's going to collect the steam. Inside here is water. Inside here is water. Inside there is water. Okay, good. So as you heat, the water will vaporize. You're dropping the water through here. You're dropping the water through this, funnel. And then, of course, once the steam forms, it rises this way, goes through this delivery tube. Now, the delivery tube goes this way. Somewhere in the delivery tube, like I said, you now have your ion filing. You have your what? Ion filing. So this, I'm taking it as the ion filing. Red hot. So that ion filing is receiving heat as well too. It's receiving what? Heat. Because it has to be red hot, like I said. Once the steam moves, and then pass over this red hot ion. In fact, let me label. This is red hot ion. as the steam passes over this red hot iron, hydrogen gas will now be produced. Hydrogen gas will now be produced. The hydrogen gas will be channeled into another vessel. The vessel contains water, just like the first one that was drawn. The vessel contains what? Water. Then you have your inverted test tube. You have your inverted test tube. You have your inverted test tube. So here we've got water. We've got water. We've got water here. Remember that the gas is collected by downward displacement of water. So this is your test tube. We've got water. Good. So what is flowing from here now is hydrogen gas. What is flowing from here now is hydrogen gas, H gas. Remember that from here steam is no longer entering because the steam has been converted from here. Yes. This red iron has reacted with the steam to produce what? Hydrogen gas. So what you now have here when the reaction is taking place is your iron 2 di-iron 3 oxide, which I mentioned. First of all, you have your red hot iron. Red hot iron. Once the steam passes over it, the steam and the red hot iron will react. If they react, the residue, that's the remnant you have here, is actually iron 2 di-iron 3. That is after the reaction. What is going further? Going further from here is now your hydrogen gas. The hydrogen gas will pass through this water, bubble through, and then be delivered upward. This is your hydrogen gas. So this is the diagram. I've told you this is water. Okay, that's water. There is nothing else here to be labeled. The main components of interest have been indicated. So just after this red hot iron, the component moving from here is now your hydrogen gas until it enters through the water, displaces the water downward, and then move upward delivery. Here, this is steam. This is steam. Let me indicate it. This is steam. Steam. This is water. This is water. Because you have water there, as you are heating, steam will now be formed. The steam will now move, pass over this red hot iron. Once the reaction takes place, the residue, the remnant here, is iron 2 di-iron 3. But that is not actually our focus. It is the hydrogen that is now produced that we talk about. So take note of this. Create a mental picture of this diagram. Create a mental picture of this diagram. Sir, is there a way of identifying gases collected from upward delivery or downward displacement faster? Yes. Yes, there is a way. But that way would also require you to do something. The way you can be able to determine whether this gas is collected by downward displacement of water or if the gas is collected by upward delivery, I would give you an assignment. And the assignment is for you to take your time. Nothing is there. You can even Google it. You can Google it. Nothing is wrong. Are you following? It's a way of you also learning. You can Google it and then read. And what do you do there? You can ask. But you can also use your textbook anyway, your hard copy textbook. Just that, of course, it's going to be faster if you just Google it. List of gases that are denser than air and those that are less dense than what? Air. And you know, you want to be specific with your gases, especially with respect to what your exam bodies are interested in. Gases like hydrogen, chlorine, oxygen gas, nitrogen gas. These 4 gases. Then ammonia gas, sulfur 4 oxide gas as well too, carbon 4 oxide gas. But sulfur 4 oxide gas and carbon 4 oxide gas we don't have much problem there. In terms of the delivery, I don't see questions being asked on them majorly. Are you getting me right? I don't see questions being asked on them majorly. But for your chlorine gas, oxygen gas, and for chlorine gas, oxygen gas, and you talk about nitrogen gas, ammonia gas, hydrogen gas, please try to know if the one that is denser than air and less dense than air. Get to know them. The ones denser than air and the ones less dense than air. So with that, it's going to guide you. Please, a moment. Hello. What's up? How are you doing? I'm taking an online class like right now. I'll let you know once I'm done. All right. Thank you. I'm sorry for the little moment out. So regarding this, I said, if you know the gases that are denser than air and the ones that are less dense than air, usually gases that are less dense than air are collected by downward displacement of water, which equates to upward delivery. Are you following, right? Upward delivery. Then the ones that are denser than air, usually they are collected by downward delivery. But if you follow our classes, I'll be revealing them to you gradually. I've told you that of hydrogen anyway, but on your own, you can go ahead. We are done with laboratory preparation of hydrogen, and this time around, we shall be turning our attention to industrial preparation of hydrogen. In the industrial preparation of hydrogen, we will be dealing with the Bosch process, that is used to produce large quantity of hydrogen gas in the industry. And of course, we shall also be looking at the concept of water gas and synthesis gas. Water gas and synthesis gas. What gas mixtures are called water gas? Is called water gas. What gas mixture is called water gas? And what gas mixture is called synthetic gas, right? Yeah. So these two gases we are going to talk about then in industrial preparation of hydrogen. Finish up. Let me wipe what is on the board, please. Remember, once you join the class, you know what to do. Share the link to your friends. Invite them to join. For GMAETS 41 students, it mustn't be that the person who joins this class must be part of our physical lesson student. This is an online class, and whenever I come on live, I try to give everybody the equal opportunity to learn, so that nobody will complain that I don't understand this from the class. I've not been taught this. Our teacher is not teaching us that. Technology has made life quite easy for you, that you can even learn independently of your physical teacher. That is how good technology has made learning to be. However, you need to respect your teachers anyway. They are doing their best. It's not easy. It's really not easy. It's not easy. But should you have challenges and other things, stick around. GMAETS 41 is here to help you in your core science subjects. Industrial preparation of hydrogen. Industrial preparation of hydrogen. Industrial preparation of hydrogen. Industrial preparation of hydrogen. This method of preparation is usually utilized for large-scale production of hydrogen gas. So in the industry, of course, you have hydrogen gas. To prepare hydrogen gas in large quantities, we go through the industrial production method. What should you know about the industrial preparation of hydrogen gas? We shall start first with the process known as the Bosch process. The Bosch process. That is the name of the process used to prepare hydrogen industrially. What happens in the Bosch process? What happens in the Bosch process? We want to give attention to that. Are we ready? You can write. In the batch process, steam is passed over red hot coke. In the batch process, steam is passed over what? Red hot coke. Red hot coke is actually carbon. Coke is an allotrope, an allotrope of carbon. So simply put, without much grammar to this, the batch process involves water, not water specifically anyway, steam, reacting with carbon. The carbon that is called coke in its red hot form. The temperature of that coke is meant to be 1200 degrees centigrade. 1200 degrees centigrade is 1200 degrees centigrade. 1200 degrees centigrade. So steam is passed over red hot coke, which the chemical formula for that guy, the symbol is carbon. So when steam is passed over carbon, something happens. A compound is formed, hydrogen is given off. That compound is an oxide of carbon, carbon 2 oxide, and then hydrogen together is produced. That gas mixture of carbon 2 oxide and hydrogen gas is what we call the water gas. Remember the process. Steam is passed over red hot what? Coke. Red hot coke is expected to be at the temperature of 1200 degrees centigrade. When steam is passed over the red hot coke, carbon 2 oxide and hydrogen gas are obtained. That mixture of carbon 2 oxide and hydrogen gas is what we call the water gas. So if your examiner asks you which of the following is known as the water gas, it's a mixture of carbon 2 oxide and hydrogen gas. But hey, take note of this. Take note of this. The carbon 2 oxide and hydrogen gas mixture called the water gas. Remember where it is obtained from. Remember where it is obtained from. It is obtained when steam passes over red hot coke. I have a reason why I am emphasizing on this. Because there is this other gas we call synthetic gas, or synthesis gas, right? That gas is also a mixture of carbon 2 oxide and hydrogen gas. But this mixture of carbon 2 oxide and hydrogen gas, the material that you get them from is no longer coke in that case. We use methane for that reaction. And we are coming to them. We are going to write out the chemical reaction. I've mentioned two gases, which are a mixture of two other gases. I mentioned water gas. Water gas, I told you, is a mixture of carbon 2 oxide, CO, and hydrogen gas. And I mentioned synthesis gas. Synthesis gas. Again, synthesis gas is a mixture of carbon 2 oxide and hydrogen gas. You see the problem? Carbon 2 oxide, hydrogen gas. Carbon 2 oxide, hydrogen gas. Both of them, this one is called water gas, this one is called synthesis gas. What differentiates both of them? Don't panic, relax. Remember, you're operating with the GMAETS 41, and you're going to get to know the difference here. Is that okay? Chemical equation will expose them. Let's get to business of the chemical equation. Remember that what I explained here is called the batch process. In the batch process, specifically, you pass steam over red hot coke at 1200 degrees centigrade. That is just basically what happens in the what? The batch process. But then, once you get the water gas, you can enrich the process. Like you can increase the production of hydrogen more by doing something. And what do you need to do? Let's try the first equation first that covered the first thing you wrote before we move on to the next thing that you have to do to enrich the hydrogen gas. So the first reaction, we said that you are passing steam. Let me write the coke first. Carbon plus steam. Steam will be in gaseous form, carbon solid. And then let's check the product. Remember I told you that carbon 2 oxide will be formed. Carbon 2 oxide, the correct chemical formula is CO. This is a gas. And then hydrogen gas will be given off. Hydrogen gas will be given off. This mixture of gases, these two gases, is what we call the water gas. The water gas. This mixture is what we call water gas. Now take note of the hydrogen obtained here. Just H2. H2. Very important in identifying water gas. The number of molecules of hydrogen there is 1 molecule. 1 molecule of hydrogen gas. Total number of atoms of hydrogen here is 2 atoms. But the number of molecule is 1 molecule. 1 molecule times 2 atoms gives you a total of 2 atoms. So in water gas, the hydrogen gas there is 1 molecule. Take note of that. This reaction is endothermic. Take note of it as well too. The formation of water gas by passing coke, by passing steam over red hot coke. The reaction is endothermic reaction. Take note. Endothermic reaction. Why do we say that this reaction is endothermic? Because remember that you need to channel heat to the system. I had mentioned that this carbon is meant to be at red hot, 1200 degrees centigrade. So you are feeding heat into the reaction system. It's an absorption process. And when heat is absorbed by a system, the reaction is endothermic. Let's continue in the explanation of the Bosch process. What happens further if you want to enrich, that is, improve, or rather increase, I mean to say. To enrich something means to increase either the volume, the amount, or the purity of that thing. In this case, how do you increase the volume of hydrogen? How do you increase the amount of hydrogen that is being produced further? What you now have to do is to react the water gas here with more steam. And that's the next information you're going to write. That is the next information you are going to what? Write. Are you following, right? That's the next information you are going. Can someone tell me where the network interfered with the class, please? Can someone indicate where the network interrupted our class? I am so sorry. I was actually in the spirit already. I was in the spirit to explain this principle, and then I forgot to check the network situation. This is so annoying. Can someone tell me where the network interfered from, please? So that I would know what to do. I've already told you, friends, network can always want to mesmerize us, but no giving up. Can someone indicate where did the network interrupt you from? Where did the network interrupt you from? Did you see this part where I explained the first process of the Bosch process? The first stage rather of the Bosch process. Did the network allow you to follow through what I explained here? Indicate, please. Did the network allow you to follow through with what I explained here? Let me know where I will just explain from. Please, I need your assistance. Did the network, when I was explaining the industrial preparation of hydrogen, and the method that is used is called the Bosch process. There are 2 stages. This is stage 1, and this is stage 2 of the process. In fact, stage 1 And then this is stage 2. Stage 2, starting from here, because this catalyst is used in stage 2. When I explained stage 1 and I told you that there you react red hot coke with steam. If you pass this steam over red hot coke, you will get carbon 2 oxide and hydrogen gas. This mixture is called the water gas. And I stated that this first stage of the reaction is called endothermic reaction. Did you understand? As in, did you follow through when I explained stage 1 of the batch process? I need yes or no, please. Someone should quickly respond. Someone should respond. You can respond by typing yes or no. Did the network allow you to follow through when I explained the first stage of the batch process? Yes or no? You can type yes or you type no. I'm waiting for your response. Did network allow you to follow through with the first stage of the batch process, which I explained? All right, so let us move on. So I've explained this and all the things you need to know. In the second stage, I told you that, or in the second stage rather, I explained that the water gas will be mixed with excess steam. Will be mixed with excess steam. The water gas will be mixed with excess steam in the presence of iron 3 oxide or chromium 3 oxide as catalyst at a temperature of 450 degrees centigrade. In the second stage of the batch process, I stated that the water gas will be mixed with excess steam in the presence of iron 3 oxide or chromium 3 oxide as a catalyst at a temperature of 450 degrees centigrade. This second stage of the reaction is to increase the amount of hydrogen being produced, so it enriches the process. And this is the chemical reaction. This is the water gas. This is your excess steam. So carbon 2 oxide will react with this steam. The steam will convert carbon 2 oxide to carbon 4 oxide. So this oxygen will be picked. By this carbon 2 oxide, you get carbon 4 oxide. And then this hydrogen will react with this hydrogen to give you 2 molecules of hydrogen gas. So this is the second stage of the batch process. Remember the things you need here. This catalyst at this temperature, any one of them, you don't use the 2 of them, any one of them. Then you have your water gas mixed with excess steam. And I mentioned that the reaction is exothermic. Heat is given out in the process. That is the summary of what I had explained earlier. I'm sorry that the network mesmerized that part. Okay? Do not give up. Remember where you find yourself, where we are, where this class is being streamed from. Here in Nigeria, all right? In Nigeria, there are challenges we face. I've always said, once you are facing that challenge, simply say, GMAETS 41, and the challenge will disappear. Okay, please, we are done with this. There is something I explained earlier. How do you remove carbon 4 oxide from this system? Because what we are trying to produce is hydrogen gas. To remove carbon 4 oxide, I actually mentioned it as a note. Further information you should know. After the second stage of the batch process, and you want to remove carbon 4 oxide to leave your hydrogen gas, what do you do? Simply, you can dissolve the carbon 4 oxide in water under a pressure of 30 atmosphere. To remove carbon 4 oxide from the second stage of the reaction, you can dissolve this carbon 4 oxide in water under pressure, a pressure of 30 atmosphere. That is one way you can remove your carbon 4 oxide. Another alternative way you can remove carbon 4 oxide is to use your caustic soda. Caustic soda serves as a solvent. You can dissolve this carbon 4 oxide in caustic soda. And if you dissolve the carbon 4 oxide in caustic soda, that carbon 4 oxide will be removed from the system. Of because it's going to react with your caustic soda, sodium hydroxide concentrated, to give you this compound. I wrote that compound earlier somewhere here. I don't know if you saw it. So that is another way you might choose to remove your carbon 4 oxide. So there are two ways I mentioned. Either of the ways can be used to remove carbon 4 oxide from this system, because what you are preparing is hydrogen gas. You can remove the carbon 4 oxide by dissolving that carbon 4 oxide in water under pressure, a pressure of 30 atmosphere, or you can remove it by dissolving it in your caustic soda, concentrated sodium hydroxide. It can absorb this carbon 4 oxide to give you this compound. Then I concluded this part by also asking, what if you still have little amount of carbon 2 oxide left in the system? Remember that this excess thing converted the carbon 2 oxide from the water gas to carbon 4 oxide. And I've told you how to remove the carbon 4 oxide. What if you still have a leftover carbon 2 oxide? How do you remove it? Let me check the network situation, please. Good. How do you remove the carbon 2 oxide if there is any other leftover? And then I mentioned that you use ammoniacal solution of copper 1 ethanoate. I wrote it on this board. Look at. I said that this board is not for you. It's for my UK students. All right. So, but I had to write something here since I didn't want to wipe this for you to still have access to it. Ammoniacal solution of copper 1 ethanoate. Ammoniacal solution of copper 1 ethanoate is used to absorb any leftover carbon 2 oxide in the Birchwood process. Ammoniacal solution of copper 1 ethanoate is simply a mixture of ammonia and copper ethanoate. So you use this compound to absorb carbon 2 oxide if you have any leftover carbon 2 oxide in the reaction process. We are done and we shall soon be rounding off anyway. You've been patient enough. You have to show your resilience. That is the spirit of GMAETS 41 when it comes to learning. Please, let us look at the alternative method to this Birch process. And whenever you hear the alternative method, which is the concluding part of our class today, in our next class we'll be looking at properties of hydrogen gas, physical property and chemical property. Physical properties and chemical properties in our next class. That could be any moment from after tomorrow. Tomorrow I might be coming on physics if care is not taken. But I might decide to maintain chemistry all through as the spirit leads. This Birch process, where you use red hot coke, has been replaced with another better and cheap, process or material. The process is still essentially the Birch approach, but the difference is that you use methane, and the gas that is formed there is not water gas anymore. So let us talk about that. I'm going to wipe the board at this point. I believe you are finished with what is on the board. You can screenshot, please. Be fast. Let me wipe it so we can round off our class. Time is against us now. So this method we are about to treat is a method that is considered to replace the Birch process. A method that is considered to replace the Birch process. The Birch process is known as the water gas process. Take note. The Birch process is known as the water gas process. So we want to look at another industrial preparation method of hydrogen gas that is similar to the Birch process, but not the Birch process. It's not called the Birch process. The Birch process is where you get the water gas. This process we're about to treat, you don't get water gas. It's just like an advanced, modified, and better process of the Birch process. Are you following, right? Good. So you can write. Let me check the network situation. All right. The Birch process has been replaced with another process that makes use of a cheaper material. That makes use of what? a cheaper material, a hydrocarbon. This process is actually the methane process. The methane process. The methane process. This methane process leads to the production of a gas known as synthesis gas. Are you following, right? Instead of the batch process that produces water gas through red hot coke, the methane process produces synthesis gas through methane. What really happens there is just that your red hot coke is replaced with methane. Your red hot coke is replaced with what? Methane. That's just it. So instead of using red hot coke as you use in the batch process, you are rather using a cheap hydrocarbon that is obtained from natural gas. Methane is the major component of natural gas. Methane is the major component of natural gas, and it is cheap to get. Yes, it's cheap to get compared to using red hot coke. So in this methane process, steam is passed over methane. Steam is passed over methane to produce a mixture of carbon dioxide and hydrogen gas. I repeat, in this methane process, steam is passed over methane to produce a mixture of carbon dioxide and hydrogen gas. So do you see the similarity to batch process? The process is very similar to batch. The only difference is that in the batch process you get water gas. In this process, methane process, you are getting synthesis gas. So I repeat again that in this process, steam is passed over methane, and a mixture of carbon dioxide and hydrogen gas is obtained called synthesis gas. Called synthesis gas. That is the first stage of the reaction. First stage of the process. Methane, which is a gas, is reacted with steam. So steam is passed over it, and then carbon dioxide and hydrogen is produced. Please let me check the network situation. I'm really all right. We are still on. I'm really concerned about the network, so we'll round up. This is the last part of our class today, by the way. Carbon will pick this oxygen to give you CO, which is a gas, and then hydrogen will react with this hydrogen, and altogether you are getting this H2 gas. However, we can balance up, and you would now see the number of molecules in this case. How many hydrogens do we have in the reactant? 4 plus 2. That 4 plus 2 will give you 6. So we have 6 hydrogens altogether in the reactant. How many hydrogens do we have in the product? 2. So to convert this to 6, ask yourself, which number will you multiply 2 by to get 6? You multiply 2 by 3 to get 6. So you fix 3 here. You fix 3 here. Permit me to plug my device, please. Let me plug this, my device. Let me plug it. As I'm plugging the device, make sure you are looking at the chemical reaction there. This mixture of gas is what we call the synthesis gas. Synthesis gas. Synthesis gas. Synthesis gas. So take note of the difference between this synthesis gas and water gas. Number 1, synthesis gas is obtained when you pass steam over what? This hydrocarbon, methane. But water gas is obtained when you pass steam over what? Red hot coke. Water gas is a mixture of carbon dioxide, CO, and 1 molecule of hydrogen gas. That is for water gas. Synthesis gas is a mixture of carbon dioxide and 3 molecules of hydrogen gas. So be guided by all these things, so that if you ask the question, which of the following gas is water gas, or which of the following gas is synthesis gas, you will know the answer to give. So this is the first stage of this methane process. The second stage. The second stage is exactly the batch process. The second stage, this is exactly This is exactly the same as the second stage of the batch process. So the second stage of the methane process is the same exactly as the second stage of the batch process, which means we expect excess steam to be mixed with the synthesis gas. In the presence of any one of the catalysts, iron 3 oxide or chromium 3 oxide, at a temperature of 450 degrees centigrade. Once you mix excess steam with synthesis gas in the presence of any of those catalysts and at that temperature of 450 degrees centigrade, you will get carbon 4 oxide and more hydrogen will be produced. So look at the reaction. I'm going to bring down the synthesis gas here. Carbon 2 oxide plus 3 molecules of hydrogen gas will be mixed with excess steam. And then we would have our product. Carbon 2 oxide, we pick this oxygen to give us carbon 4 oxide. And then plus the hydrogen gas that will be produced. More hydrogens will be produced. Remember here it is 3 molecules of hydrogen, altogether 6 atoms in the first stage. In the second stage now, you have this hydrogen and this hydrogen, so H2. And of course, you can balance up the reaction. This is 6 hydrogens plus 2 hydrogens, giving you 8 hydrogens. To balance up, we fix 4 here. This is an enriched, more quantities of hydrogen gas. You can remove this carbon 4 oxide, like I explained earlier, by either dissolving it in water under pressure of 30 atmosphere, or you can absorb it using your caustic soda, sodium hydroxide. If you have any leftover carbon 2 oxide, from the synthesis gas, what do? Absorb it using your ammoniacal solution of copper 1 ethanoate. Remember, like I told you, the second stage of this methane process is exactly the same as the second stage of the batch process. So, as we conclude this, take note that in the industrial preparation of hydrogen, you can use the batch process or use the methane process. The batch process leads to the formation of water gas first, which is a mixture of carbon 2 oxide and one molecule of hydrogen gas. You can enrich the process. Okay, the first stage of the reaction has produced the hydrogen gas you are looking for, but you can decide to enrich the process, increase more quantity of the hydrogen gas. To do that, you will need to react excess steam with the water gas, which converts the carbon 2 oxide in the water gas to carbon 4 oxide and then gives you more quantity of hydrogen gas, which of course is 3 molecules there, 3 molecules or 2 molecules rather. 2 molecules of hydrogen gas. Okay, in the second stage of the batch process. In the methane process, the first stage of methane process is different from the first stage of batch process, but they follow the same pattern. Each of them makes use of steam. But in the methane process, you pass steam over your methane. Whereas in batch process, you are passing steam over red hot coke. In the methane process, the mixture of gas produced, carbon 2 oxide and hydrogen gas, is called synthesis gas. Take note of how many molecules of hydrogen gas in the synthesis gas. 3 molecules, unlike the 1 molecule in the water gas. You can still enrich the process, similar to what we saw in the batch process exactly. So what have we learned today generally in our class? Just as a quick summary, we focused on preparation of hydrogen gas. We started by talking about who discovered hydrogen gas, Lavoisier. Who discovered hydrogen gas, Cavendish. Who named it hydrogen, which means water former, Lavoisier, due to the flammable nature of hydrogen gas with air. Of course, when it mixes up with air, you see droplets of water. We went ahead to look at the laboratory methods of preparing hydrogen gas. We discussed 3 of the methods, where we talk about the action of metal on mineral acid. We picked zinc as a metal there, reacting with the mineral acid, hydrochloric acid. And then, of course, we saw the reaction equation. Zinc chloride was formed and hydrogen gas was given off. We went ahead to talk about method 2 of preparing hydrogen in the laboratory, where we explained that sodium reacts with what? Cold water. And that reaction is vigorous. When sodium acts on cold water, hydrogen gas will be given off. The resulting solution, I said, will be alkaline in nature because that resulting solution is sodium hydroxide. We now talked about the third method of preparing hydrogen gas in the laboratory, where iron acts on steam. The reaction between red hot iron with steam leads to the production of hydrogen gas. And don't forget the residual solid there. Iron 2 diiron 3 oxide is the residual solid. In all cases, hydrogen is collected by upward delivery, which is the same as downward displacement of water. And I emphasize that it's because hydrogen is less dense than air. It's lighter than air. And I told you that hydrogen is one of the known most lightest substance. So it's collected by downward displacement of water, which is the same as upward delivery. We saw the various diagrams. I told you to take note, create a mental picture of each of the diagrams. And then we went ahead to the industrial preparation, which we just concluded, the batch process, the methane process. In the batch process, we met a mixture of carbon 2 oxide and one molecule of water, of hydrogen rather. Carbon 2 oxide, one molecule of hydrogen, which we call water gas. And of course, the methane process, we have a mixture of carbon 2 oxide again and 3 molecules of hydrogen gas called the synthesis gas. While the batch process uses red hot coke, the methane process uses what? Methane. In both cases, steam is passed over these materials or these substances. Remember the catalyst you use in the second stage of each of the industrial method of preparing hydrogen. We talked about chromium 3 oxide or iron 3 oxide at 450 degrees centigrade. Don't forget how to absorb your carbon 4 oxide. You can use maybe water, dissolving the carbon 4 oxide in water under pressure of 30 atmosphere, or you can use your caustic soda to dissolve that carbon 4 oxide. And if there is a leftover carbon 2 oxide, don't forget that you can use ammoniacal solution of copper 1 ethanoate to absorb that carbon 2 oxide if there is any left over. In conclusion, I want to also state that in the industrial preparation of hydrogen, we can prepare hydrogen through electrolysis method. I repeat, we can prepare hydrogen industrially through electrolysis method.